Now, part C is the one that a lot of people struggle with. And the idea here is computing the dimension of the span of the inner product. And if we're looking at what does it mean for V to be in the perpendicular space of the span of A, B. And here, this means that V is equal to, or the inner product of V with C1A plus C2B is equal to 0 for all C1 and C2 in the real numbers. Now, the challenge with this is we wanted to somehow get to a dimensionality argument from this information. And there's a little trick here that was challenging for some, that this is equal to C1VA plus C2VB equaling 0. And now we claim if we let C1 equal 1 and C2 equal 0, then VA must be, the inner product of V with A must equal 0. And let C1 equal 0 and C2 equal 1, this gives us that VB must equal 0. So the inner product of V with A must equal 0, and the inner product of V with B equals 0. Note that if the inner product of VA equals 0 and the inner product of VB equals 0, then the inner product of V with C1A plus C2B will also equal 0. Therefore, V is in this span of the set AB, or in the is perpendicular to the span of vectors A and B, if and only if V inner product with A equals 0 and V inner product with B equals 0. Now, what's interesting about this, or what's so nice about this, is that this means that if we expand this out, we get that V1 x1 plus V2 x2 plus V3 x3 equals 0, and V1 y1 plus V2 y2 plus V3 y3 equals 0. So we have a homogeneous system of equations using the vectors x1, x2, and x3. And if we look at that homogeneous system of equations, where the dimension of the space is the number of free variables. So given a solution set to a system or a homogeneous system of equations, the span or the dimension of the solution space the solution space is the number of free variables and the number of basic variables is the number of linearly independent rows. For the first one, if I scroll up, if they're collinear, so if I look at one with them being collinear, if A and B are collinear, then our system of equations, which I'm just gonna C, B, just gonna copy out here. Here has 0 or 1 linearly independent rows. Because if they're both the 0 vector, then there's 0 linearly independent rows. But if one of the vectors is non-zero, then there's 1 linearly. This means that there are 0 or 1 basic variables. This would result in 3 or 2 free variables, meaning the dimension of the space is 3 or 2, respectively. So if we're collinear, then our dimension is 3 or 2. Now, what if we're linear? If A and B are not collinear, then our system of equations has 2 basic variables and 1 free variable. Therefore, it has, or our space has dimension 1.